So I wanted to run some quick numbers to compare what the expected temperature of the sauna is versus what I was actually observing. Uh, so I'll start off with the overall heat transfer equation. And I'll explain this in a second so that it makes a little bit more sense. But if we start with our control volume, which is the sauna in this case, I'll connect those. Okay. So what I'm looking for is that there's some point where the heat in, call that Q in, balances with the Q out. That's the heat lost. So this is heat from my heater. This is just me having a cheap sauna. But there's some equilibrium point where the temperature inside is, sorry, not the temperature inside, the heat in matches the heat out. So just from personal experience, you can understand that when there's a greater difference in temperature between two rooms, you lose more heat. If the rooms are larger, you lose more heat. And if they're not insulated very well, this U value increases and you lose more heat. So applying the dimensions that Amazon gave me, it's about 6 foot tall by 3 foot deep by 3 foot wide. We can calculate the area, and I'll go out of order a little bit. But we see there are 4 walls, and they're each 6 foot by 3 foot. So that gives us 72, hold the page, feet squared. And then we have a top and a bottom. That's 2 times 3 by 3. And it's not completely fair because the bottom's on a ground, which is not exposed like the top would be. But we have 18 feet squared. And so summing these, we get 90 feet squared. And just a tip for any kind of heat transfer or fluids problem, physics, pretty much anything, it is a lot easier to use metric units versus imperial, because imperial units are kind of weird, like having, for example, pounds mass versus pounds force, or it would otherwise make more sense to just have kilograms for mass or newtons for force, or it's usually a lot cleaner. So what I end up doing is the dimensions are given me in feet. I'll calculate it in feet, in this case feet squared, and then just convert it later on. So that is equivalent to 8.36 meters squared. And yeah, just to keep it clean. All right, then for our U, which is our overall heat transfer coefficient, we have, for our overall heat transfer coefficient, that's really just a way to combine, if you have conduction, convection, it helps measure how much heat is lost due to that. So in this case, there technically is convection from the heater since it has a fan, but inside the sauna, there isn't much air movement, or at least doesn't feel like there's much air movement. So I'm just simplifying the problem and saying that it loses heat through conduction, which might not be completely fair, but we'll run through the numbers that way anyways. So since I'm just doing simple conduction through what I'm assuming is one layer of insulation, that is equal to K over L, which is the conductivity of our insulation versus how thick it is. So as your insulation gets thicker, your U value goes down, and therefore you lose less heat. So in this case, we have 2 layers of cotton, according to Amazon. A layer of cotton has a conductivity of, oh, it's actually 0.029 watts per meter squared Kelvin. That might not make a ton of sense right now. I'm assuming that's about 2 millimeters thick, and there's 2 layers of it. So if we go down here, we can work out the units a little bit better. And I find it easier to write it this way. Works better for me to go horizontally versus having stuff vertical like this. So it's the same thing. And I need to convert this to meters. So over here, we say there's 1,000 millimeters per meter. And so see our units cancel. To cancel, you have to have it in the numerator and denominator. Okay. So this actually should be in meters. I goofed here. But so in this case, 9 divided by 2 times 1,000, and there's 2 layers of insulation. See those cancel. So our overall heat transfer coefficient is 29 watts per meter squared Kelvin. See, since that's not supposed to be there, there's 2 meters in the denominator. Okay. So, and down here, our Q, this is just what the heater is rated to. So whenever you look one up on Amazon or buy it in the store, on the packaging, it'll tell you how many watts it's rated to. In this case, I have a 1500 watt heater. And last input is our ambient temperature. And that's in Kelvin, as you can see here. And room temperature in Kelvin is about 293. And that's Celsius plus 273 degrees. For Fahrenheit, it's probably something goofier. But okay, if we expand this equation down here, our delta in temperature is sauna minus ambient. And we need to rearrange it for this variable. So we say T sauna equals Q over UA plus T ambient. And down here, so that's 1500 watts divided by this value, 29 watts per meter squared Kelvin, times 8.36 meters squared. And this has to cancel out to Kelvin, since we're adding a Kelvin. Okay, so we'll see, this has to cancel out and just leave us with Kelvin, since we're adding another term that's in Kelvin. And you can see that these cancel, and having it in the denominator here is the same thing as it being up top. So this is about 6 Kelvin if you calculate it, and our ambient is 293 Kelvin, so our total is about 300 Kelvin. And if you look it up on Google, that's around 80 degrees Fahrenheit. I'll circle that. So, interesting to note that this is a lot smaller than the value that I observe in the sauna. When I'm in the sauna, it feels like it gets to, well, I know it gets over 100. So it's worth going back and double checking that these numbers are right. But a quick intuitive check is that this is in the approximate ballpark. It's not like this value came out to be like 2,000 or something ridiculous. But okay, what did we learn? So the way I can get the sauna hotter ultimately is to either make the ambient temperature greater, which means I run my house heater and crank that up, which is expensive. I'm not doing that. You make the sauna smaller, which I'm also not doing that because I have a set size. Like I bought a sauna, I'm leaving the dimensions the same. I buy a bigger space heater, which my space heater, the value I've recorded it reaching is about 250 Fahrenheit, which is plenty because I only want my sauna to go to like 175-ish. So what makes the most sense, according to the math, is to just insulate the sauna better. And you can see theoretically if you went infinite thickness on your insulation, the amount of heat lost technically goes to zero. And if you do the math, this number does explode. Like it's like off the charts high, but in real life there's limitations with what temperature your heater, whatever your QN actually can be.